Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel. Today's topic of discussion is switches as applied to electrically controlled systems. Our objective today is to review important switch terminology and introduce and examine several different types of switches, as well as discuss the concept of switches held in their activated state in the deenergized start state of an electrically controlled system. This lecture is intended to be a continuation of the Switches and Series Circuits lecture all the way back in the Basic Electronics 1 DC Circuit Analysis playlist. If you haven't watched this lecture yet, or perhaps only dimly recall its contents, by all means take the time to do so now. This lecture's purpose is to review and expand upon this basic content and apply this material to electrically controlled systems. Recall that a switch is a simple electromechanical device that serves as the principal digital input to an electrically controlled system. A switch can be closed or open, and never a little bit of both or halfway in between. Switches can only be placed in one of two mutually exclusive binary states, opened or closed. A normally open pressure switch, for example, changes to the closed state when pressure exceeds a certain preset value. Sensors, in contrast, are analog in nature, in that their electrical output is infinitely variant within a given range and varies in proportion to the measured quantity. A pressure sensor, sometimes called a pressure transducer, will output more voltage or more current as pressure increases. Later lectures at the Big Bad Tech channel will discuss sensors in greater detail. Recall that over the course of the Basic Electronics 1 DC Circuit Analysis playlist, I spared no effort in expounding upon the observed electrical characteristics of open and closed switches. An ideal open switch, idealized as an infinite resistance, will not allow current to flow. Depending upon its position in a circuit, an open switch will have a voltage drop across it. In contrast, an ideal closed switch is idealized as a 0 ohm resistor, which will allow current to flow. Being idealized as a 0 ohm resistor, this closed switch should have no voltage drop across its two terminals. Although in practice, a real closed switch does present a measurably small amount of resistance and therefore might experience a tiny voltage drop, especially when carrying large amounts of current. If these facts do come as a surprise to you, or if you are even the slightest bit confused, I am asking you reconsider your intentions about the electrically controlled systems playlist because you are fundamentally unprepared to discuss its contents. Again, the electrically controlled systems playlist is based upon your successful completion of all other previous prerequisites, and you cannot proceed without an intrinsic understanding of basic electrical properties like Ohm's law, Kirchhoff's voltage law, Kirchhoff's current law, basic series and basic parallel circuit properties, and the expected and observed electrical properties of open and closed switches. This being said, I'd like to perform a quick review of the common terminology used to characterize switches before I hit you with a bunch of confusing schematics. Among the terms we'll review are poles, throws, electrical isolation, actuation, deactivated versus activated, deenergized versus energized, normally open versus normally closed, mechanical interlocks, and momentary versus maintained. Recall that a pole is the moving portion of a switch. A throw is the number of different connections the pole can make. Here is the schematic symbol for an individual single pole, single throw, SPST, toggle switch. It has a single moving portion, hence the term single pole. The single pole has a single connection it can make, hence the term single throw. A number of independent SPST switches can be housed in the same package, where each one is electrically isolated from and is capable of being closed and opened independently of the others. Each switch is therefore an independent and isolated entity in no way, shape, or form connected to any other switch. The package would exactly be that, a package. It just holds a collection of switches together. Don't confuse the package with an individual switch. An application for an SPST toggle switch would be to energize a load when it's closed and de-energize it when it's open. Consider a single pole double throw switch, SPDT. This switch also has a single pole. However, this single pole can be placed in one of two different positions, hence the term double throw. This single pole double throw switch has a central terminal on the left that is not electrically isolated from, but rather serves as the common terminal for both the other two terminals on the right. An application for a single pole double throw switch would be to de-energize one load at the same time a different load is energized. Additionally, one could use a single pole double throw switch to selectively supply a single load from two different sources. Consider a subtle modification to the single pole double throw switch by including a stable center state in which no connection is made. This is now a single pole triple throw switch, sometimes called an SP3T-CO, where CO stands for center off. There is still a single pole, however it can make three different connections. Consider a double pole single throw switch. This is like two independent single pole single throw independent switches ganged together, the only difference being that these two poles close or open simultaneously with a single action. Although mechanically linked, that's what the dotted line is supposed to represent, the two terminals of the top switch are still electrically isolated from the two terminals of the bottom switch. The mechanical linkage's only purpose is to close and open both switches simultaneously. There are two poles, hence the term double pole, and each pole can make one connection, hence the term single throw. An application for a double pole single throw switch would be to simultaneously energize two loads. Consider a double pole double throw switch, DP-DT. This is just like two ganged single pole double throw switches mechanically linked with a single action. The top single pole double throw switch is electrically isolated from the bottom switch. However, the terminal on the left is now the common servicing both terminals on the right for the associated switch. The mechanical linkage's only purpose is to transfer contacts simultaneously. There are two poles, hence the term double pole, and each pole can make one of two connections, hence the term double throw. Consider a triple pole single throw switch, 3PST. This is like three independent single pole single throw switches ganged together, the only difference being that these three poles close or open simultaneously with a single action. Although mechanically linked, that's what the dotted line is supposed to represent. Each switch is still electrically isolated from every other switch. The mechanical linkage's only purpose is to close and open all three contacts simultaneously. An application for a triple pole single throw switch would be a three-phase contactor designed to start or stop an industrial three-phase AC motor. There are three poles, hence the term triple pole, and each pole can make a single connection, hence the term single throw. If you're sensing a pattern developing, you're not the only one, because I could go on all day like this. Here's the key to the pattern, and use this key to guide your studies. Poles are the number of moving contacts controlled by one action. Single pole devices, like the single pole single throw, single pole double throw, and single pole triple throw with center off, have one moving contact. Double pole devices, like the double pole single throw and the double pole double throw devices, have two moving contacts. Triple pole devices, like the triple pole single throw switch, have three moving contacts. Throws are the number of positions each pole can connect with. Single throw devices, like the single pole single throw, double pole single throw, and triple pole single throw, have one throw each moving contact. Double throw devices, like the single pole double throw and double pole double throw switch, have two mutually exclusive connections for each pole. Triple throw devices, like the single pole triple throw with center off, have three positions each pole can connect to. Moving on, let's review three important switch characteristics: that of their actuation method, their natural deactivated state, and activation period. Actuation method. This distinction is generally divided between manual and automatic or mechanical means. A manually actuated switch might be a push button, a lever, or a handle, basically something you hit with your hands or maybe your feet if you're sufficiently dexterous. An ESTOP, a push button, a selector switch, or a drum or cam switch might be good examples of manually actuated switches. An automatic or mechanical switch is something that doesn't require the presence of human hands or feet to hit. Such automated devices allow continuous function without constant human input or attention. Examples might be a limit switch, a pressure switch, a temperature switch, a rotational speed switch, a proximity switch, or a photoelectric device. We'll introduce and examine a number of different types of switches and their common schematic symbols in a moment.